Our next operation is set difference. So again, I've got my running example going. When we do the set difference, basically what we're doing is we're restricting our universe. And so what we call this is finding the complement of C relative to S. So I want to think of S as my new restricted universe, and I'm going to look for the complement of C inside of S. We also call this the set difference of S and C. So here is my Venn diagram, and so this yellow shaded region is my set difference. Now we're going to write this with a subtraction sign, but I want you to be careful not to say minus. We subtract numbers, not sets, okay? So this is the complement of C relative to S. In general, if I've got sets A and B, the complement of A relative to B is the set of all x such that x is in B and x is not in A. Remember, the not is what we think of when we're talking about complements. Okay, like I said, don't call this minus. It's set difference. Okay, so it's an operation on sets, not on numbers. So here's the Venn diagram, and you should notice that this shaded region is the complement of A relative to B, but we could also describe this set as B intersect with A complement. So that's where that complement of A relative to B comes from. All right, so let's try finding some set differences. So the first set difference I want to find is A without B, or the complement of B relative to A. So what you want to do is think of restricting A as your universe, and I want to list the things in A that are not in B. So here, notice B, C, and D all live in B. So the complement of B relative to A is just the empty set. There's nothing in A that's not in B. What about the complement of A relative to B? So now I want to think of my universe as B, and I'm looking to list the elements of B that are not in A. So I just go through my elements. A is not in A, so that's going to be in this set difference. B is in A, C is in A, D is in A, E and F are not. So E, F go in the set. What about the complement of the complement of C relative to B? So here again, B is my universe. So I'm thinking of this as my universe, and then C is the set that I'm taking the complement of relative to B. Okay, so I want to list the things in B that are not in C. Here, A, B, C all live in C, and so I'm left with D, E, F. And finally, I want the complement of B relative to C. So C is my universe. Always the first set you want to think of as your universe now. So I want to list the things in C that are not in B. In this case, everything in C lives in B, so this is going to be the empty set again. All right, so let's look at some properties of set operations. And these properties are going to pop up all semester, okay? So the first property is called the commutative property. If I have two sets, it doesn't matter what order I take their intersection or their union in. So A intersect B is the same as B intersect A, and similarly for their union. The associative property allows me to reassociate when I'm taking operations on three sets. So if I want to do A intersect B intersect C, I can first do A intersect B and then intersect that with C, or I could first do B intersect C and then intersect that with A. Similarly with the unions. I can distribute intersection over unions. So if I want to take A intersected with the set B union C, I can think of distributing this intersection over that union. So I take A intersect B unioned with A intersect C.